So we're now looking at the concept of acceleration. What is accelerated motion? Accelerated motion is when an object either speeds up or slows down, or movement where an object turns. This one's a bit of a weird one. So the speed up, slow down, that's fairly understandable. But what about, why is it when an object turns, we consider that to be acceleration? Well, first of all, we have to understand what causes acceleration are forces. So normally, objects either will stay put at rest, or they tend to want to keep going in a straight line at a constant speed. So the way I like to think about this is the coffee test. So this is the idea where you have a coffee, a very full coffee in the cup holder of your car. So here's our little virtual coffee. And let's say the coffee is just filled right to the brim here, right? So there's the coffee level just underneath the edge of the cup. All right, so now as you're driving, or I should say when you are parked, the coffee just sits normal, not a big deal. However, if you start backing up, so let's say the front of the car is in that direction, all right? So if you put the car in reverse and you go a little bit too aggressively, the coffee will all of a sudden start to spill out this way. And the reason why is the coffee wants to stay put or do whatever it was doing before. So the coffee was initially at rest. It really wants to stay there. That's what it wants to do. So if you accelerate too quickly towards the reverse, right, it's going to come over top of the lip and then you get a bit of a spill. Same thing happens if you put the car in gear in the forward direction and you accelerate a little too aggressively. If you accelerate a little too aggressively, the coffee wants to stay where it was. The cup is dragged forward, so the coffee then spills out back this way. All right. So that accounts for the speeding up, the slowing down business. But now you also know that if you're driving and all of a sudden you take too hard of a turn, a similar thing happens. So now let's say we're coming up to the intersection and say this is our forward motion here. And then we need to make a right turn. So we turn right. Now, if we turn right really, really aggressively with our full cup of coffee, and why you don't have a lid on it, I don't understand. But if you turn really aggressively to the right, you know that it's going to appear to spill to the left. Conversely, if you pull out and accelerate aggressively to the left, the coffee pours out to the right. The fact that the coffee moves or appears to jump out of the cup is evidence that we are experiencing acceleration. So what's actually happening here? Well, for this, we have to do a bird's eye view, or what I mean by a bird's eye view is looking from above down onto the ground. So I suppose if we want to update this to a modern era, a drone's view. So let's say we have a curve in the road like this, and your vehicle is going in this direction here. When you make your turn like this, whatever is inside your vehicle, including your coffee, really wants to keep going in its original trajectory. So your car veers left, but the coffee wants to keep going straight. And if you go too quickly, the coffee cup can't hold on with enough force to prevent it from spilling over. And as a result, as you turn left, the coffee appears to spill to the right. And that is evidence that we are experiencing acceleration. So let's take a look at another couple of examples. A car accelerates from 0 kilometers an hour to 100 kilometers per hour in 60 seconds. So here we have an example of a vehicle speeding up. Now, you know that the longer this takes, the more gentle the acceleration. The shorter the time, the more aggressive the acceleration. Another example, consider a ball rolling down a hill. As the ball speeds up, the distance increases between the time intervals. So if the time between each of these images is the same, as time goes on, it covers more ground in the same amount of time. And that is further evidence that we are experiencing acceleration. So let's take a look at the formulas. This is a very similar formula triangle that we had for constant motion, but the variables change slightly. Let's take a look at this one. We have delta V. Delta V refers to the change in our speed. The vector version is the change in velocity. So the change in velocity versus the change in speed. Now, if you recall, velocity has a direction where speed does not. In both cases, that change is measured in meters per second. A stands for the acceleration, either the scalar version or the vector version, and it is usually measured in meters per second squared. We'll talk about this unit in a minute, what this meters per second squared business means. And then the delta t is the change in time, and it's usually in seconds as well. So this unit, meters per second squared, it's a bit of a strange unit. The better way to look at it is like this, the meters per second, or simply the change in the speed over time. So if you have an acceleration of 10 meters per second squared, what that means is that the speed increases by 10 meters per second every single second. So we have a little chart here to show that. So at the 0 second mark, we haven't moved yet. But after 1 second, our speed is now 10 meters per second. And the reason why is that we've increased our speed by 10 meters per second. Then after another second, we're traveling at 20 meters per second. Therefore, we added another 10 meters per second, and so on and so forth. So by the time the third second rolls around, we're traveling at about 30 meters per second. Just to give you some context of what 30 meters per second is, 30 meters per second is equal to 108 kilometers per hour. So this would be going from 0 to 108 in 3 seconds. Incidentally, this number, 10 meters per second squared, is actually a very close approximation to what the acceleration due to gravity is. The acceleration due to gravity on Earth is 9.8 approximately meters per second squared. So this means after about 3 seconds of free fall, you are traveling at highway speeds. Of course, this is ignoring air resistance and all that stuff, but we'll get into a little bit of that later. Okay, so for the first example, we're going to interpret these velocity versus time graphs. Okay, so the acceleration formula is actually simply just the slope of this graph. So the acceleration is actually equal to the slope, and the slope is, as you recall, the rise over the run. But the more precise definition was our delta y over delta x. However, in this graph, it's not the y-axis, but the v-axis. So this is actually your delta v, and the x-axis is actually the t-axis. So that's delta t. So that's how we get acceleration is equal to the change in v over the change in t. So let's interpret the graph itself. So first thing, you want to find the velocity of the object at the 12-second mark. So again, you go along the x-axis and you find the 12-second mark. So each dash here represents 2 seconds. So this would be 2, 4, 6, 8, 2, 4, 6, 8, 10. And then here we have 12, 14, 16, 18, 20, so on and so forth. So here we are. This would be the 12-second mark, and draw a line straight up to the slope right here. And then from this point, draw a horizontal line to the y-axis, which is actually the v-axis. And once you've done that, you now read what this point here is on the v-axis. Well, according to the scale, if this is 0 meters per second, and that's 5 meters per second, each of these lines represents 1 meter per second. So this would be 1, 2, 3 meters per second. And then you follow through with the rest. So you go to the 40-second mark, go up to the graph, and then read the value off the axis. Now, to find, for example, our change in velocity, we simply take those two numbers and we subtract them. So that would be 10 minus 3, which would be equal to our 7 meters per second. Now, when we're asked to find the time interval, well, that is the amount of time to go from here to here. And again, it's just simply subtracting these two numbers. So that would be your 40 minus your 12. So your exercise for today is to complete the questions on this first plot and then repeat for the second plot a little bit later here. And then we have these homework questions over here.